Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on to a new type of hypothesis test called the chi-squared test for independence and homogeneity. The chi-squared test for independence and homogeneity is not only a new hypothesis test for us, but it's actually a new type of hypothesis test in general. The chi-squared test for independence and homogeneity is what is called a global hypothesis test. And actually, the remaining hypothesis tests that we're going to be talking about in this course, the chi-squared test for independence and homogeneity that this set of videos will cover, the chi-squared test for goodness of fit, which we'll be covering in the next set of videos, and the ANOVA, or analysis of variance test, that will be our very last topic of our course, are all examples of global hypothesis tests. So you might ask yourself, what is a global hypothesis test compared to all the ones we've been doing previously? Well, a global hypothesis test is a hypothesis test that tests for some sort of general change or general relationship. It isn't as specific as some of the ones that we've been doing in the past, where oftentimes we assert a particular direction, like we think the average has increased or we think the percentage has decreased. Instead, global hypothesis tests for global changes or global relationships present in the data. So, as we will sort of go through and see with the chi-square test for independence and homogeneity and the later hypothesis tests that we'll be talking about in later videos, we'll always see that the alternate hypothesis is always sort of preset for us. There's always just going to be one alternate or one claim that is used because we're not testing for a specific type of relationship or a specific type of change. We're just looking for a change or relationship in general. So let's get in and talk about the specifics of this test. The chi-square test for independence and homogeneity is used when you want to investigate if a relationship exists between two categorical variables. So the first thing that we want to sort of keep in mind here is that this hypothesis test is used to investigate for a relationship between two categorical variables. So we're continuing sort of working with categorical variables, but now we're not working with a percentage that's associated with a categorical variable. Instead, we're trying to determine if a relationship exists between these two variables. You'll notice that there's no longer a limitation on the categorical variables have to be Boolean or binomial. So now the categorical variables can have as many categories as you would like. One other thing to sort of remember is way back earlier around exam 2, we talked about a sort of very introductory way into investigating relationships between categorical variables. And specifically, we talked about a way of displaying information for a pair of categorical variables. So if you will remember, anytime we have information where a sample has been categorized according to two categorical variables, this means that the data will be presented to you guys in a two-way table. So a good trick for identifying if you're supposed to use a chi-square test for independence and homogeneity is by looking for data that is presented in a two-way table. That is a major tip-off that this is the appropriate test to use. All right, so even though it is a sort of new type of hypothesis test, it still follows that same 5 main step procedure. So let's talk about what the hypotheses are going to look like. For a chi-square test for independence and homogeneity, the hypotheses are not written out mathematically, they're more written out as sentences. So the baseline or null hypothesis is that the two variables are not related. This should make sense, right? If we just pick out two random variables, right? If we just think of two random categorical variables, maybe we think of something like hair color and choice of educational major. Our initial thought would be that those two variables are not going to be related. If you think that they are related, it would be on you to provide evidence for that. So our null hypothesis is always going to be that the two variables are not related. The alternate, or the claim, is always going to be that the two variables are related. So in other words, we're trying to find evidence for the claim, trying to find evidence for the relationship here. Now, this chi-squared procedure does have a little bit of an intermediate step. So this intermediate step is what's called constructing the expected counts table. Whenever we're talking about the expected counts, we're going to use the abbreviation EC. When you're constructing this expected counts table, you're going to be using this formula. Each expected count is equal to their row total times their column total divided by the table total. And in a moment, when we get to our first example, we'll see exactly what this formula is really doing and make more sense of it. But just be aware there's sort of an intermediate step here in between the hypotheses and the conditions, where we construct what is called the expected counts table. All right, let's look at the conditions here. For the conditions, the first two conditions are our standard ones. The sample must be random and representative, so it must be good statistical data, and the sample size must be less than 5% of the population size. The third condition relates to these expected counts. We need less than 20% of the expected counts, smaller than 5. In other words, what this is basically saying is we can't have too many really small expected counts. If all of the expected counts are greater than 5, then condition 3 is going to be all good. The only concern is if a lot of them are smaller than 5. So we require that less than 20% of the expected counts smaller than 5. All right, let's talk about the test statistic here. So the test statistic is a different type of statistic here. It's not a Z or T. It is what is called a chi-squared test statistic, which is sort of where the name comes from. So chi is sort of written as a little bit of a loopy X. So this chi-squared statistic is the sum of the difference between the observed counts and the expected counts squared divided by the expected counts. So as just a note here, that OC, those are what we call the observed counts. That's your actual data. That is what you observed happen. That's basically how many people fell into each category in your two-way table. And the expected counts, well, the EC, those are your expected counts. That's what you've determined in that step 1.5, right? So that expected counts is exactly what you're doing in this right here. Okay, so let's go ahead and talk about the p-value. Since it's a different type of test statistic here, right? It's a chi-squared, we will need to use a different statistical table. So when you go to calculate the p-value, you'll be using table D, which can be found in your table, your statistical table PDF. So it'll be table D, which is the table for the chi-squared test statistic. Table D does have a degrees of freedom. I'm just going to quickly flip over to there so we can take a quick look at it. So table D looks like this. You have degrees of freedom here, and you have your p-value here. You read it very similarly to how we dealt with table C. You'll find where you fall between. So maybe you have 3 degrees of freedom, and you have a test statistic that's 8. So 8 would put you in between 7.81 and 9.35, and then you just go right up here, and that would tell you that your p-value would be between that 0.025 and that 0.05. So we read table D very similarly to how we read table C. How do you determine the degrees of freedom? Well, the degrees of freedom are a bit different for a chi-squared. It's not based on the amount of data. It's actually based on the amount of options that you give for the two different variables. So what we do is we look at the two-way table, and we take the number of rows minus 1 times the number of columns minus 1. Now, another way to think about the number of rows and the number of columns is to realize that the number of rows is the number of choices in the first variable, and the number of columns is the number of choices in the second variable. So again, the degrees of freedom here is based on how many different categories each of the variables actually has. Step 5, the conclusion, always the same for every hypothesis test we cover in this class. If the p-value is small, smaller than alpha, we will be rejecting HO, which means we have significant evidence for our claim. Notice that in this case, because the claim is already preset, that would mean that if we reject HO in a chi-squared test for independence and homogeneity, that means we do have significant evidence that the variables are related. When the p-value is larger than alpha, that means we will be failing to reject HO, as always, which means we do not have evidence for our claim, which, again, because the claim is already preset in this type of hypothesis test, that means we will not have evidence that the variables are related. So let's jump right in and take a look at an example of running this chi-squared test for independence and homogeneity. All right, so for our example of this, we're going to suppose that we have a university that has around 30,000 students, and they're trying to study if their students' choice of major is related to their level of satisfaction with the school. So to study this, the university randomly selects 400 students, records their major, and then surveys them on how satisfied they are with the university. And they give them 3 options: very satisfied, satisfied, and not satisfied. And they get the following data. So they classified their students as majoring in physical sciences, social sciences, or arts and humanities. And then they had very satisfied, satisfied, and not satisfied. Remember, the way to read this two-way table is that each of these values in here are the amount of people that had both of these traits. So there were 35 students who were majoring in physical sciences and were very satisfied. There were 48 students who were majoring in social sciences and were satisfied, so on and so forth. Remember, when we first introduced two-way tables, we said computationally, before you get into doing anything, you always want to go ahead and get all your row and column totals. So let's go ahead and do that with first getting our row totals. So it looks like we should get 81. So we had 81 physical science students overall. Then 63, 48, and 45. Looks like we had 156 social science students. And then 75, 40, and 48. We had 163 arts and humanities. Then 35, 63, and 75. 173 people were very satisfied. 19, 48, and 40. 107 were satisfied. And 27, 45, and 48. Looks like 120 were not satisfied. Now, if we total those totals up either way, 173, 107, and 120, or 81, 156, and 163, you can check on your calculator, or you can just look back here and realize that we selected 400 students, so this has to total up to 400. So, as always, whenever you see a two-way table, definitely want to add on all the row, column, and table totals. So what we want to do in part A is we want to carry out at alpha equals 0.05 a hypothesis test to test the claim that the choice of major is related to level of satisfaction for students at this university. So notice that we're testing a claim about whether or not the choice of major, which is a categorical variable, is related to level of satisfaction, which is a categorical variable. Relationship between two categorical variables tells you that we're talking about a chi-squared test for independence and homogeneity. So for part A here, this will be a chi-squared test, and we'll usually abbreviate this for independence, IND, and homogeneity, HOM. Okay, so let's go ahead and start with our hypotheses. So for the hypotheses here, the null hypothesis is that the two variables are unrelated. We should say what those two variables are, so we would say choice of major and level of satisfaction are not related. So that's our baseline assumption, right? These are just for us two random variables, choice of major and level of satisfaction. As far as we know, without any study or any evidence or any data, they're not related. What's our claim or what's our alternate? Well, simply that they are related. So choice of major and level of satisfaction are related. So this is always what these hypotheses are going to look like. The null is always going to be that things are not related. The alternate is always going to be that they are related. This does make setting up the hypotheses for a chi-squared test for independence and homogeneity a bit easier than setting up the hypotheses for some of the other tests. All right, now we're going to do that intermediate step. We're going to come up with our expected counts table. So the expected counts table is we're going to recreate this table, but we're going to say what we expected to see in each of these spots rather than what we actually observed. It's an expected counts table. So we'll just quickly abbreviate. We've got physical sciences, social sciences, arts and humanities. We have very satisfied, satisfied, and not satisfied. So we're going to fill in 9 values here for those 9 different elements in there. So we're just recreating the inside of the table. How do we find each of these? Well, when you pick a position in your expected counts table, you want to use that formula of row total times column total divided by table total. So for this first position here, what we're going to do is we're going to take the row total, which would be 81, times the column total, which would be 173, and then divide by 400. So we will be taking 81 times 173 divided by 400. And what you should get is you should get about 35.0. And I will keep one decimal place. The reason I'm going to keep a decimal place is that it makes it easier in the long run to identify what's observed and what's expected, because obviously the observed counts, the actual data, are always going to be whole numbers, but the expectation, what we think should happen, could just be a decimal because it's just a theoretical value. All right, how do we get this guy here? Well, the row total will still be 81, but the column total will be 107. So we'll be taking 81 times 107 and then dividing by 400. So 81 times 107 divided by 400. Looks like you should get 21.7. And finally, for this guy right here, what we're going to be doing is row total 81, column total 120. So 81 times 120 divided by the table total, which is 400. So we should get 24.3. Now, we don't need to worry about these totals out here, but just to make sure you guys sort of have a sense of what the expected counts table is doing, if you add these up, if you add up 35.0, 21.7, and 24.3, you are still going to get 81. The reason is we're not saying that we expected different amounts of physical science students. We're saying that this is how we think they should have been distributed if there was no relationship between their choice of major and level of satisfaction. So we were expecting 35 of the physical sciences students to be very satisfied. Notice that that matched very much what we saw. We were expecting 21.7 to be satisfied. We only saw 19, so a very slight difference. And for not satisfied, we were expecting 24.3, and we actually got 27. We're not saying that we expected a different amount of physical science students overall. We're saying that we expected that they might be distributed differently. That's what we're really looking at here. All right, now let's go ahead and fill in these values here. So for this guy here, we're going to be taking the row total 156, column total 173, and then dividing by that 400. So 156 times 173 divided by 400. Looks like that guy should come out as 67.5. For the next one here, this guy right there, we'll be taking 156 times 107 divided by 400. So we've got 156 times 107 divided by 400. And looks like we should have 41.7 there. And then finally, for this guy here, we'll do 156 times 120 divided by 400. So 156 times 120 divided by 400. And looks like we should get 46.8. Again, you go ahead and you can check 67.5 plus 41.7 plus 46.8. Still going to be 156. We're just saying that this is how they should have been distributed if there was no relationship. Because remember, as we're doing our computations, we're always working under the assumption that the null hypothesis is true. For our last row, for this guy here, we'll be taking 163 times 173 divided by 400. So 163 times 173 divided by 400. You should get 70.5. Then for this position here, we'll take 163 times 107 divided by 400. So 163 times 107 divided by 400. You should get 43.6. And then finally, for the very last one here, we'll take 163 times 120 divided by 400. And looks like we should get 48.9. Once again, you sum up any of these rows, you're going to get the same row total. You sum up any of the columns, you get the same column total. We're not saying the total should change. We're just saying how they were distributed amongst the different combinations might change. All right, now we can go ahead and talk about our conditions here. So for the conditions, we had to have random and representative. That was stated. It was a random sample, so we're all good. The second condition, our sample size needs to be less than 5% of our population size. Well, we know that our sample size was 400. Do we know our population size? Well, it did say that there were about 30,000 students, so we can actually check this directly. N equals 400. Is that less than 0.05 of 30,000? Well, 0.05 of 30,000 is equal to 1,500. 400 is less than 1,500, so we're all good. Finally, for condition 3, we want less than 20% of the expected counts. smaller than 5. So let's look at our expected counts. They're right here. We built 1, 2, 3, 4, 5, 6, 7, 8, 9 different expected counts. The lowest expected count we got was 21.7. None of them were smaller than 5, so we're all good. If you want to write that out mathematically, we'd say that we had 0 expected counts out of 9 expected counts were less than 5. That's 0%, which is less than 20%, so we are all good. Would it have been okay if one of them had been less than 5? Say this 21.7 had came out as like 1.7. Well, that would be less than 5, and then this would have been 1 out of 9. One expected count out of the 9 that we built would be less than 5. 1 out of 9 is about 11%, and that would be less than 20%, so we'd be all good. What about if this guy was like 1.7 and this guy was 4.3? Then 2 out of the 9 counts would be less than 5. 2 out of 9 is about 22%, and that would not be less than 20%, and then we'd be stuck in condition 3, wouldn't be satisfied. But in this case, we built 9 different counts. None of them were smaller than 5, so we are all good here. In general, if all the expected counts are large values, condition 3, you're going to be all good. All right, let's move on to the next page, and we'll go ahead and do our computation here with our test statistic. So for part 3 here, we need to go ahead and do our test statistic. All right, so for our test statistic, what we want to do is, actually, we're going to go back real quick. We're going to actually carry over our data. So I think we'll go ahead, we'll bring this over so just we can keep our actual data here. There you go. All right, so for step 3, we're going to go ahead and do our test statistic. And we want to do this chi-squared is the sum of the observed counts minus the expected counts squared over the expected counts. All right, now, if we go back onto our previous page here, we just determined all the expected counts. So I'm going to just grab this and bring this over here. Okay, because we'll definitely want this. So just bring that guy over to here. Okay, there's our expected counts table. So that's going to tell us about these guys. Where do we get these observed counts? Well, that's our data. So we're going to just remember that these are going to be our observed counts. So let's go ahead and actually start calculating. We're going to have to sum this up for every one of the instances in our table. There's 9 things in our table, so we're going to have 9 computations to do here. So the first one is that we observed 35 physical science majors who were very satisfied, and we expected to get 35. So our first computation would be 35 for the observed count minus 35.0 squared divided by the expected count, 35.0. Then we're going to add, and we're going to do that for this one. We observed 19 physical science majors who were satisfied. So we had an observed count of 19. We expected 21.7, so we're going to subtract 21.7. We'll square that and then divide by the expected amount, 21.7. Then we'll move to the next one. We observed 27 physical science majors who were not satisfied. We expected 24.3. So 27 minus 24.3 squared divided by 24.3. Then we'll move on to the next row. So we observe 63 versus an expectation of 67.5. So 63 minus 67.5 squared divided by 67.5. Then plus we observed 48 against an expectation of 41.7. So 48 minus 41.7 squared over 41.7. And then we observed 45 against an expectation of 46.8. So 45 minus 46.8 squared over 46.8. Plus, now we're on to our last row. We observed 75 versus an expectation of 70.5. So 75 minus 70.5 squared divided by 70.5 plus we observed 40 against an expectation of 43.6. So 40 minus 43.6 squared over 43.6. And then finally, we observed 48 against an expectation of 48.9. So 48 minus 48.9 squared over 48.9. So calculating a chi-squared statistic is one of the most computationally intensive one. None of these computations are particularly bad, but it is a little bit hassle-some to have to go through and write out all of these and actually calculate them. When you guys are doing this on your own, if you want to skip writing out all these formulas, that's okay. What I would like to see, though, is what we write next, which is the result of each of these 9 computations. So we're going to type these in. The first one, 35 minus 35.0 squared, well, that's going to just come out as 0. So we're going to get 0 plus. Next one, 19 minus 21.7, then square the result, then divide by 21.7. Now, because every one of these has a square in it, every one of these is always going to be positive. So every contributing part of the test statistic is always going to be positive. So you should get 0.34 for that one. Next one, parentheses 27 minus 24.3, square that, and then divide by 24.3. You should get plus 0.3. Next one, 63 minus 67.5, squared, divided by 67.5. You should get 0.3. Plus 48 minus 41.7, squared, divided by 41.7, you get 0.95, and then 45 minus 46.8 squared divided by 46.8 looks like 0.07. Then 75 minus 70.5 squared divided by 70.5 looks like you should get 0.29 plus 40 minus 43.6 squared divided by 43.6. Looks like you should get 0.30. And then finally, 48 minus 48.9 squared divided by 48.9. Looks like you should get 0.02. So when you guys are writing this out on your own, you can definitely skip writing all this as long as you're comfortable with the formula. But we will want to see this portion where we show the result of each of those computations. Now we'll go ahead and actually sum all those together and get our chi-squared value. So 0.34 plus 0.3 plus 0.3 plus 0.95 plus 0.07 plus 0.29 plus 0.30 plus 0.02. So we get a chi-squared here of 2.57. All right, now we are ready to go ahead and find our p-value. So this will be step 4 here. So we need to get our p-value. We're going to be using table D, and our degrees of freedom here. Well, if we look back, we had 3 rows and 3 columns. So the degrees of freedom here will be 3 minus 1, number of rows minus 1, times number of columns minus 1. So 3 minus 1 times 3 minus 1, that's 2 times 2. So our degrees of freedom here is going to be 4. So our chi-squared is that 2.57, and we have 4 degrees of freedom. So let's go find that on table D. Again, 2.57 as our test statistic. So there is our degrees of freedom 4. Notice that the first value is 5.39, so we end up right here. So we don't even make it onto the table in this case. Now, as usual, as you go this way, you'll notice that the p-values get smaller and smaller. Ours then must be larger than the largest p-value here. So we just figured out that our p-value, because we didn't even make it onto the table, is going to be larger than 0.25. So in this case, we would say that our p-value is greater than 0.25. Then we can go ahead and make our conclusion here. So we take that p-value, we compare it against the alpha of 0.05. The p-value is larger than 0.25, so certainly it is larger than 0.05. So we got a large p-value here. that means we would fail to reject HO. So if we go back, right, to where we actually wrote out our hypotheses, we see no reason to throw this guy out. And this guy was that the choice of major and level of satisfaction are not related. So that means we failed to find evidence for our alternate, which was that choice of major and level of satisfaction are related. So we would say fail to reject HO, no significant evidence that choice of major and level of satisfaction are related. So there's no evidence that these variables are related. Now, real quickly, let's just think about in real life whether or not like a university would be excited about that finding, right? That there was no evidence that these things were related. Does this mean that the university has a lot of happy students? Well, not necessarily, right? This doesn't say that people have a high level of satisfaction. Does this mean that the university has a lot of unhappy students? Again, no, has nothing to do with the amount or how many people are satisfied. This is just saying that choice of major is not related to level of satisfaction. And probably that would be a positive conclusion, because this is basically saying that the university seems to be doing an equal job with all of its students, right? If we had found that choice of major and level of satisfaction are related, that might indicate that the university is doing a better job with certain majors than it is with others. Now, of course, that could be an issue since most universities would probably want to sort of be treating all of their students equally here. So even though we didn't find evidence for a relationship, that actually might be viewed as sort of a positive conclusion here. We might be glad that all the students are having a generally similar experience. Now, whether or not that similar experience is a good experience, bad experience, okay experience, we don't really know. It just doesn't seem to be that your choice of major has an impact on that. Okay, so this is your guys' first example of running this chi-squared hypothesis test, this chi-squared test for independence and homogeneity. And again, it's always going to be used when we see our information presented in a two-way table like that. That's your main tip-off to know when to run this procedure. Let's go ahead and quickly discuss the type 1 and type 2 errors in this situation. So let's go ahead and grab our hypotheses, just because we always want those whenever we're doing sort of error analysis. So I'll just grab these guys real quick. Alrighty. Okay, so let's go ahead and do the errors here. So this will be part B. Let's go ahead and just erase that. All right, so we'll get that guy there. Okay, those were our hypotheses. So let's think about what a type 1 error would look like here. So a type 1 error, as we know, is where we reject HO, but HO is true. So as always, when we're writing these, let's just try to say each part separately. So rejecting HO and HO is true. So rejecting HO in this case would be throwing this out and saying that these things are related. So rejecting HO would be, we'd say we have significant evidence that choice of major and level of satisfaction are related, right? Because that would be throwing out that they're not related and going with that they are related. But HO is true, well, meaning they are not related. So we'd say, when in reality, they are not related. So, again, type 1 errors, generally false positives. You think something is going on when it really isn't, and that's exactly what we're describing here. This is where we think we have significant evidence that the choice of major and level of satisfaction are related. We think there's a relationship, when in reality, they are not related. All right, let's go ahead and talk about the type 2 as well. Type 2 error, again, in general, that's a fail to reject HO, but HO is false. So this is where the decision we make is to fail to reject HO, but HO is actually false. So what would it mean to fail to reject HO? Well, that means that we failed to throw this out. We failed to find evidence for a relationship. So we'd say we have no evidence that choice of major and level of satisfaction are related. That would be our decision, when in reality, well, HO is actually false, so this is wrong, and they really are related. So, when in reality, there we go, they are related. So, as usual, right, when we talk about a sort of, when we talk about type 2s in general, we usually call them sort of missed effects. So in this case, right, we're saying that we don't think that there's a relationship between these two variables, but in reality, there is a relationship, and we missed it. So that's our typical type 2 error there. All right, so that's showing you guys some of the error analysis, standard error analysis, just applied to our new hypothesis test. All right, let's do one last thing. We wanted to build a confidence interval here. So if we go and we wanted to do, for part C, we want to do a 95% confidence interval for the percentage of very satisfied students at this university. Now, it's sort of interesting to sort of ask ourselves what type of confidence interval is this going to be. At the beginning of this video, we introduced a new hypothesis test, but we didn't introduce any new confidence intervals. So that means that the confidence interval that's going to be used here must be one of the confidence intervals we've already learned. Well, what are we trying to estimate here? We're trying to estimate a percentage of very satisfied students at this university. So we're estimating a single percentage. So this is going to be a one sample proportion confidence interval. Now, you might say, well, why are we able to just throw all the students together? Didn't we have several different types of students? Didn't we have physical science students, social science students, and arts and humanities? Well, if you think about it, that's part of what we learned in Part A. In Part A, we found that there was no relationship between their major and their level of satisfaction. In other words, knowing their major didn't impact their level of satisfaction. So that means that we're safe in sort of combining all of the students together. If in Part A, we had found that your choice of major really was related to your level of satisfaction, then we'd probably want to build separate confidence intervals for the physical science students, for the arts and humanities students, and for the social science students, because we'd think that they would be different. But we actually found that there was no relationship, so we're safe in sort of lumping everybody together here. So we're going to do a one sample proportion confidence interval. Now, for the conditions, well, obviously those first two are already checked because those are the ones just debate about the sort of usefulness of the data, the fact that it's statistically appropriate data. The third condition for that one sample proportion confidence interval is that the successes and failures are both greater than or equal to 10. So let's figure out what counts as successes and what counts as failures. So we'll go back to our original data here. Now again, we're trying to build an interval for the percentage of people who are very satisfied. So we know that 173 total students were very satisfied. And anybody who was satisfied or not satisfied, all of those count as failures because we're just looking at the percentage who is very satisfied. So our successes would be the 173. And our failures would be the 107 and 120, which I guess would be something like 227. So 173 successes, 227 failures, and a sample size of 400, because we're just looking at the overall sample here. So if we go back here, our successes, like we said, 173. So that's greater than or equal, it was 173, I believe, right? Yep, 173. That is greater than or equal to 10, so we're all good there. And our failures, we said that that was going to be 227, which was also greater than or equal to 10. And of course, if you check 173 plus 227, that does total up to 400, which it has to because we know that that's our sample size there. Okay, so let's go ahead to our construction then. For our construction here, we are going to be using p hat plus or minus z star square root p hat 1 minus p hat over n. If we go ahead and take a look at that, we need three things, p hat, n, and z star. For p hat, well, that's going to be your successes divided by your sample size, so 173 over 400. So 173 divided by 400. Looks like that would come out as approximately 0.433. So 43.3% of students in our sample were very satisfied. N was 400, and Z star, well, we looked that up on table C. Z star confidence level 95%, but we've done this guy a bunch. We know that this is 1.960. Okay, let's throw everything in there then. 0.433 plus or minus 1.960 square root 0.433, 1 minus 0.433 divided by 400. We'll go ahead and get that margin of error first. So 1.960 times the square root, parentheses 0.433 times 1 minus 0.433 divided by 400. And it looks like our margin of error should come out as plus or minus 0.049. Then we go ahead and do our subtraction, 0.433 minus 0.049. That would be 0.384, and then 0.433 plus 0.049, and that would be 0.482. So we would interpret this as normal, 95% confident that between 38.4% and 48.2% of these university students are very satisfied. So we're saying anywhere from about 38% to about 48% of the student population are very satisfied with with their program. Now, again, the sort of thing that I wanted you guys to see here from a computational side of things, we haven't learned any new confidence intervals, so we had to go back to the ones that we had already seen. We were just trying to estimate a single percentage, so that told us a one sample proportion confidence interval. More importantly, in terms of the behind-the-scenes stuff, in terms of like a real-life application, the fact that we found that major was not related to level of satisfaction is what allowed us to just throw all the students together regardless of their major and just look at the percentage of the students that were very satisfied. Had we found that there was a relationship, what we probably would have done is built separate confidence intervals for each major separately, since we would have learned that, well, the major was an important determining factor in terms of level of satisfaction. In our next video, we'll take a look at another example of running this chi-squared test for independence and homogeneity.